Might as well get started. Got 30 seconds until the official time, but since the gravitas has been established. So I'm Baron Schwartz. Welcome, everyone. Thanks for coming out. Is anyone else a little bit hoarse from last night's Google party? It was quite a little shindig there with a lot of noise. I don't know about you. I'm a little bit taller than most people, and when there's a really noisy event like that, I have a really hard time hearing people because they're talking at my sternum, you know. I have to kind of do this. Okay, so go ahead and get started. I'll just introduce myself real quickly. My company is Percona. I didn't found the company. I just work for it. And we do training, support, development, services, engineering for MySQL. And we also run a series of MySQL conferences called Percona Live. And the next one is in London on October 24th. Beyond that, we have one scheduled in Washington, D.C. on January 11th, or perhaps 12th. I might have that wrong. And after that, in April, from the 10th until the 12th, out in Santa Clara, California, we've rented out the whole Santa Clara Hyatt Convention Center, which is the location of the traditional MySQL conference. O'Reilly's not doing the MySQL conference again this year, so we went ahead and stepped in, and we're going to continue that tradition. So here's today's agenda. I'm just going to divide the talk today into two major sections. One is about how to look at TCP traffic on a system and figure out what's going on the system without looking at anything more than arrivals and completions of queries or HTTP requests or whatever it is. We'll get into that in a little bit. And then in the second part, I'm going to show you how you can actually model scalability and performance, which are actually different things. And you can model that out beyond what you can observe just by looking at TCP packets arriving and departing from the system. So this is a little bit of why I do this, you know, why I write talks like this, why I deliver them, why I do this sort of research into the math of TCP and system performance. You can't optimize what you can't measure, and I spent a lot of my life measuring systems. Spent a lot of my time trying to figure out what's going wrong with systems and troubleshooting them. And I've developed just a whole series of different tools and approaches for doing that. Not only have I developed them, but for the most part, I'd say 95% of what I do, I've learned from other people, not developed it myself. So this is one of those techniques that I use to observe what's going on first before I try and explain it or make guesses about it. So the process that I'm going to show you here today is to observe the system in a very lightweight and cheap way that doesn't even require access to privileged data that you can normally get very easily. There's lots and lots of performance models, such as queuing theory using the Erlang C functions and so forth, that require extensive effort. Just to give you a little bit of a sense of the difference here, the contrast between what I'll show you today, where all we're doing is just sniffing a little bit of TCP traffic and modeling it, versus the traditional queuing theory, which is highly related to what I do today. In queuing theory, you have to not only gather very carefully defined measurements, but you have to ensure that the system behaves according to a very strict set of requirements, including there has to be a certain distribution of inter-arrival times and all of these kinds of things. And if these things don't hold true, then the model simply doesn't apply. And the math is much, much more complicated and harder to explain and harder to understand and apply. What I'll show you today is just drop dead simple. So the first thing that I try and do is observe, and observe carefully and with experience, but not in a difficult way. Then I use that to explain, and after spending 95% of my time gathering evidence and measuring a system, then the solution to whatever problem I'm trying to solve is normally obvious. And this really is like a 95% effort, as opposed to the trial and error method of troubleshooting, where you see something and then you try and change something, and you have no idea whether that was really what solves the problem or not. So the reason that I observe first in a lightweight way is that I don't know often what kinds of problems may be happening on a system. Somebody may call me in and say, the system is behaving badly, and in the end, we may resolve 3 problems, not 1. So it's very common that there's some kind of misconfiguration in the system. There's some kind of misconfiguration of MySQL, for example, or there's a component in MySQL that's behaving badly. It's also common that the supporting environment, like the disks, are behaving badly or are oversaturated, or there are other things happening on the system, like somebody's running a really expensive cron job. And there can also be non-scalable parts within the system itself. I'll give you just one example. One of the customers that I helped, and this is not an extraordinary example. This is a very commonplace example. They had scalability problems inside of InnoDB, and they had misconfiguration, and the query cache inside of MySQL was behaving badly, which it tends to do. So it was 3 problems that we solved. So back to TCP. You can measure this. I've just been speaking about MySQL because that's my domain of expertise, but you can do this with any system that has a call and response TCP semantics. There's only one database I know of that I know does not do that, and that's MongoDB if you configure it in fire and forget mode, where you send a query to the database server and you don't wait for the response. If that's true, you won't be able to observe at the TCP level how long that query actually took to process inside of the database server. But most databases, and in fact most other systems such as web servers and Memcached and lots of special purpose programs, send a message to the server and then block and wait for the response back to the server. So this call and response TCP semantics means that you can actually see the arrival time and the completion time, and you can use that to measure how long the query executed, or the request, whether it's a query or not, the request executed on the server. So from that, we can derive several of the fundamental metrics of performance. The most fundamental metrics that we can use as building blocks to build up all of these other types of metrics are the arrival times and the completion time. So if we see packets going to the server and coming back, and we correlate the source and destination ports, we can see this packet corresponds to the beginning of this request, and then the response packet corresponds to the end or the completion of the request. And we know that pair of packets constitutes one request. And so from that, with the arrival time and the completion time, of course, we can subtract them, and we get the execution time. We also know the observation interval, the point of time that we started observing the system to the point of time that we stopped observing the system. We know the busy time, which is the period of time within the observation interval that there were requests executing on the system. And we know the total execution time just by summing up all of the execution times within the observation interval. We can also use Little's Law, and we can derive a couple more things from that. We can look at concurrency on the system and the utilization of the system. Utilization and the busy time of the system are a little bit different. I'll show you a graph here in a moment that'll make that clear. So here's, at the TCP level, this is what we actually do. This is just using widely available tools, nothing fancy here. I'm just giving some arguments to TCP dump to make it print out one line per packet, and abbreviating that as much as possible, but at the same time giving it a high-resolution timestamp. So just let me walk through the options that I'm giving at TCP dump here. The -S is what they call the snapshot length. That's the number of bytes of the TCP payload that I want to capture. 384 is the length of the IP headers and the TCP headers. So all I'm capturing here is the packet headers. I'm not looking at anything inside of the TCP payload. And in fact, I don't need to know anything about it. Sometimes it's helpful to, of course, if you want to look at what the query was or something like that. But for the purposes of sort of application agnostic modeling of systems, we don't need to know that. We don't need to know what query it was or anything. All we need to know was the packet arrival and response times. I actually have a little bit of a typo on here. That should be TCP port 3306 for MySQL. 5432 is for PostgreSQL. Sorry about that. The -I any option just says bind to all of the interfaces, all of the NICs on the server. -N&Q says to not try and resolve host names and to be quiet, one line per packet. And then the 4 T's are the timestamp formatting options. So as a result, we get what you see on the bottom of the screen here. And just reading from top to bottom, we have the timestamp the date and time with microsecond precision of one packet coming into the server from 10.220.146.79 and port 35805. And the right angle bracket there says that that's the origin. And it's going to 10.119.42.41, port 3306, which is MySQL listening. And the last little bit there says TCP 83, which is the actual length of the payload, minus the packet's header. So there's another 83 bytes here that we didn't capture, but we don't care about it. The next line underneath of that is actually the response from, no, I'm sorry. Yep, the next line underneath of that is actually the response back from port 3306 on the server to port 35805 on the client, and then we see another incoming packet, which I didn't show you the response for. So this is all we need. We just need these packet headers from TCP dump. And then there's a tool in Percona Toolkit, which is available on percona.com/software. It's open source. It's just it's a Perl program. And we can just run PT TCP model on this file and redirect the output. And what it does is it goes through the TCP dump output and finds and correlates the inbound and outbound port numbers, as I just showed you, and then prints them out one per line. So instead of 2 lines per request, one representing the start and one representing the completion, we have 1 line per request. And here I'm printing out the timestamp converted to a Unix timestamp format so that you can do math on it easily, of the beginning and the end of the request, the elapsed time, just the subtraction of those two, and then the host and port number, which from this point on we completely ignore. Okay? We don't care which host it was, we don't care which port it was, all we care about is the arrival and completion timestamps. And you do this, capture 30 seconds, excuse me, capture 5 minutes, capture some representative portion of your traffic. I'm going to be showing you, throughout this talk, I'm going to be showing you one 30-second sample of data. Every example that I use here will show you the exact same 30-second sample of data. It comes from one of our customers, comes from a rather overloaded server running on Amazon EC2. It's a MySQL server. So after you process the TCP traffic that you captured, you get a file with a bunch of these lines in it showing you the arrival and completion timestamps. So what can you do with this? Without any further processing, you can already do a lot of really interesting stuff on this. So I'll walk you through a series of plots. Visualization is an incredibly powerful tool. You have one of the most sophisticated computers in the world sitting right inside of your head. And it's not just your brain, by the way, but it's your eyes. Your eyes are really sophisticated computers. And you can look at data, you can look at a plot, and you can see things that would take you a really long time to find staring at numbers scrolling down your screen, staring at a terminal full of stuff. If you think you're good at reading the matrix, you should plot the matrix instead, and the woman in the red dress will become very obvious. Right? So here's the first thing that I do. All I'm doing is plotting the arrival time versus the execution time. I'm sorry, I'm plotting the completion time versus the execution time of all of those requests in this 30-second period of time here. So the horizontal axis going from left to right is time. That's 30 seconds worth of time on the bottom of the graph there. And then the execution time of the request goes from top to bottom. So at the top, near the center, you can see that there's a request that took about 1/3 of a second, just under 3/10 of a second, to execute. There's a bunch of others that are kind of scattered across the plot. And then there's the overwhelming majority of these requests executed in less than 200 microseconds, and they're clustered along the bottom in basically a solid red bar. So I think there are interesting patterns already on this. Audience participation, anybody want to say what they see on it? Yes, sir. Yeah, so, yeah. I'm sorry, can you say the last bit? The vertical orientation, the pattern of sort of vertical trails coming down the screen, that's not an artifact. That's actually in the data. So that was what I hoped somebody would see and volunteer to say. Yes, sir? So the question is this a cron script running on intervals? This is only 30 seconds worth of data here. And there's nothing really happening on the server other than database queries.
Is the red mark indicative of the end of the response or the beginning?
So the question is the red mark indicative of the end of the response or the beginning? And it's the end. So these are the completion timestamps of the requests. So I'll show you something on the next slide that's interesting. You may have noticed this, but you weren't sure whether it was your eyes or not. But those spikes of long-running queries are actually slanted. It's not completely vertical. It's tilted to the left just a little bit. Does anybody want to guess what's going on? Yes, sir, in the back.
One long-running query that queues up all of the smaller queries that finish after.
Exactly. So we have one long-running query that blocks other queries from completing. When it completes, the other queries that are queued up behind it can then proceed to completion. And that's why we see, for example, our friend, the 0.3 of a second query completing. And then after that, somebody else completes. There are two queries that complete about 0.2 of a second. And then a few others that complete just after that. So what we can see is that halfway down that spike where there were two queries that executed in 0.2 of a second or so, what happened was that they really arrived 1/10 of a second after the 0.3 of a second query began. So they had been waiting for 0.2 of a second, more or less. We can't really tell unless we plot the arrival timestamps. But they had arrived and then queued up and executed with a total time of about 0.2 of a second. Now there's a difference between the total response time, which we can see here, has two components in it. Total response time is composed of queue time, which is time spent waiting to do your work, and then the service time, which is the time that you spent actually doing your work. From this, we cannot tell what the service time of those queries was. We can only tell what the total execution time was. We don't know how long that they were queued up before they got to actually access the resources that they wanted and go ahead and do their work. Anybody want to guess what kind of queries these are? Okay, spoiler alert, they're select for update queries. This particular database server has a processing queue inside of the server. And somebody is running select for update. A bunch of other select for updates are coming along and scanning into the table and then hitting that locked row and blocking there and waiting until the first query completes and releases its locks. I'll skip this slide. That's for people who are looking at these slides later online. So the stall detection, did I miss something? No, I didn't. Stall detection like that works based on the completions. If there's a stall and causes something else to block up behind a particular request that has some resource, that holds some resource exclusively, then maybe we can plot the completions and see what's affecting or see what's going on, see more evidence about what's happening. So let me first plot the arrivals. And here I'm not plotting individual arrivals. I'm actually grouping them into buckets per 5 milliseconds. Along the bottom of the graph, we have time, as before. But the vertical axis now is a count of arrivals per 5 milliseconds. So for every 5 milliseconds, somewhere here in the middle, we can see that there was a point of time, a 5 millisecond period of time where there were approximately 34, 32, something like that, arrivals in that 5 millisecond time period. So what do you see in this plot? Any interesting patterns here? I don't. I just see noise. But if we do completions, there's something a little bit more interesting, I think. So the completions per 5 milliseconds shows us that there looks like there's maybe some pattern going on, but definitely towards the left there's a spike of completions. And the interesting thing is that this is in a different place than we saw before. I'll show you these two graphs superimposed on each other later, but that spike of completions on the left there, that is not correlated well with all of those other ladies in the red dress, matrix kinds of things that were on the previous graph that we were looking at. So completions, again, becomes the place where we can see evidence of something going on. But it's hard to see what might be going on other than this one very suspicious spike. It may be that we're doing something like we're grouping maybe 5 milliseconds is too fine of a granularity. Maybe we need to go to 10 milliseconds or half a second or something like that to get a better look at what's happening. So I want to dig further into this. At this point, I'll just stop and say these these are the kinds of techniques that I use to drill into systems and find the performance problems that exist. And I need to say there that if you drill into systems far enough, you will find performance problems, because computers are networks of state machines, of resources, and queues between them. And the nature of computers processing things is that they queue. It happens. I mean, it may happen at a level that's really egregious and obvious, but even in a well-running system, it happens at a very fine granularity. And if you dig down far enough, you will find the problems. I'll talk a little bit more about that later. So is there really a problem? You know, the arrivals looked pretty uniform. The completions looked like there was a suspicious spike. Is there really something that, you know, is there a problem in this system that we care about? So the following graph that I'm about to show you is at 0.2 of a second, not 5 milliseconds. I changed the granularity to make things a little bit more obvious. So here's arrivals again. And here's completions again. And I'll flip back, arrivals, completions. Can you see any difference? There actually is a difference. So here's where the human brain computer is actually starting to fall on its face a little bit. It's very hard to look at these things and see the difference. We need to do something a little bit different to the data to pull out the signal within that noise. What I'm trying to do in all of these things is find the signal within the noise, because there's a lot of noise in computers. So if we want to look at the difference between arrivals and completions, we should use subtraction. So I'll just do subtraction. And that spike that we saw before now becomes extremely obvious. So let's think about this subtraction, completions minus arrivals. What we're really looking at here is a spike that doesn't just go up, but it first goes down, which means that there were very few completions relative to arrivals there. And then it goes very, very high up, which means that there were lots and lots of completions relative to arrivals. So basically, completions were the things that got stalled, essentially. What this means is that the arrivals more or less continue to come into the system with a random distribution. There's a particular distribution. It's called a Gaussian distribution or a Poisson distribution, depending on whether you're looking at the timestamps or the time between the arrivals. And that basically means that the queries coming into the system are not dependent on each other. They're uncorrelated. And we see basically random noise coming into the system, but we see a strong correlation of things departing the system. And the subtraction makes that extremely obvious. So there's something going on here. Something happened on this system that caused queries to suddenly stop completing for a little while and then continue again. And again, this is different from what we saw before. I'm plotting the first graph in blue now, and I'm plotting my completions minus arrivals in red. And you can see that the spikes that we saw in the first graph don't really line up that strongly. You know, there appear to be different mechanisms at work here. It's not just one kind of a thing happening on this system. So there may be one problem that's causing two symptoms, or it may be two kinds of problems that are happening on this system. The big spike in the red line on the left, I do not think was caused by select for update. I didn't capture the queries themselves, so I can't go back and prove that. However, if I had captured the full payload, I would be able to prove whether or not that was from select for update or not. But I happen to know that there were several different problems on this server that were causing these sorts of things. So I've just given you sort of a whirlwind tour of my favorite Pileup detection algorithm. So this is something that you can use not only to go into a system that you know has problems, but you can go and look at a system that you're not really familiar with, and you don't know whether it has any problems or not. And you can say, is there a problem on this system? And what you do is you aggregate at a finer and finer interval until you find these spikes, and you will find them. And at that point, you can start asking the question like, well, is a 0.2 second pileup actually acceptable? For a system that is running most queries in 200 microseconds or less, no, it's not really. But 0.2 of a second, depending on what kind of a query it might be, that might not be a bad experience for the user. However, what I will say is that this starts to show problems that may be latent and are building slowly and will eventually intrude into your awareness in the form of bad user experience. And it's very helpful to be able to find these things and notice before problems become serious. There's another great pileup detection algorithm that I want to show you, or a poor quality of service detection algorithm that I want to show you. And that's the index of dispersion. This is also called the variance to mean ratio because that's what it is. It's simply the variance of the query response times divided by the mean of the query response times, again, aggregated into some buckets of time, some little intervals. So the index of dispersion is very useful as opposed to lots of other aggregate metrics because it's dimensionless. It's not exactly dimensionless, but the dimensions are comparable from one system to another. There are lots of other metrics that you could use, like the 95th percentile, which is very helpful for certain purposes, or the standard deviation, which is very helpful for certain purposes. But those things tend to be not comparable from one system to another. So, for example, a standard deviation has the magnitude of the source data. If there's a standard deviation over a distribution of response times of 1 second, if you plot that over the response times, you will see that they correlate very well. If there are queries that are typically running in 10 seconds, you will see standard deviations in the tens of seconds. If there are queries that are typically running in the microseconds, you'll see standard deviations in the microseconds. Okay? So it helps to have something that doesn't have the dimensions of the source data so that we can compare different workloads to each other as a unit rather than as a unit of time. So if we compute the index of dispersion over, again, the same input in 5 millisecond buckets, we see some spikes. Again, interesting spikes. What the index of dispersion really shows you is how variable the response time is. And you can see this with the standard deviation, but again, the magnitude varies depending on the input. Here, the magnitude is relative to the mean. So we have a couple of spikes, one that goes almost up to 10. So the index of dispersion here is 10 times what the normal kind of index of dispersion is, which is very, very small. Most of the time, these queries are completing relatively uniformly. And indeed, there's a very simple workload on this server relative to some kinds of workloads that we might see. So there are 3 significant areas here where the response time was highly variable. And a spike up to 10 is really highly variable. It's very significant. It's not unusual. I mean, I've seen spikes of variation up to an index of dispersion of 20, 30, 50, 100 sometimes. But 10 is still significant. So what does it mean when there's a spike? It means that it's highly variable, and highly variable performance is bad. Good quality of service is uniform quality of service. Good performance is uniform performance. Right? We want our systems to perform uniformly and predictably with low latency and low variation. The other thing that highly variable response time means is that there's likely a very good opportunity for optimization. Because things that are variable means that sometimes things are probably executing differently. Maybe choosing a different index and maybe not choosing an index at all. Maybe choosing a completely different query plan, something like that. So whenever you see something that is highly variable, it might mean that there is a particular subset of the queries that you're bunching together that could be optimized to use a different index or to behave more like the unwashed masses of queries that complete very quickly and uniformly. Here's the collection of all of the plots that we've looked at so far. And again, this is all simple time series plotting. I'll take a moment and tell you that I use GNUplot to do this. You can also use R. There's lots of plotting tools that you can use. I encourage you to get familiar with a command line tool like GNUplot or R because they're so much faster than spreadsheets. They can operate on raw text data. They know how to just slurp in lines and treat each number on the line as a positional variable. They don't have to be, it doesn't force you to define columns or anything like that. And each of these plots took me, I don't know, I mean, I fooled around with the data a little bit, but this is, I could plot this in less time than it took to tell you about it, certainly. Most of these plots take a split second to generate. So it's extremely useful to get familiar with a tool like GNUplot or R. R is much more powerful. I would say GNUplot is perhaps more accessible to the beginner, which is why I learned it. I've run into the limitations of GNUplot a time or two and wished that I knew R, but R is a whole different beast. R is a little bit complicated to learn, although extremely powerful. So this concludes the first portion of our flight. You can put your tray tables up and we'll take off to the second portion, which is scalability and performance. And this is a formal definition of scalability and a formal definition of performance. This is not scalability sort of described loosely as a synonym for capacity or load or all of these different kinds of things. It's fine to talk about those things in casual conversation, but if you want to model them, you actually have to have a definition of them. So what is scalability? It's actually a mathematical function. It's not complicated. Don't run yet. And the x-axis changes from time. All of that earlier stuff was time series. But here we start to change it to concurrency. Low concurrency at the left and high concurrency at the right. And then the y-axis is throughput, or queries per second. So here's our scalability function with one point plotted. That's one unit of something. Maybe it's one server, maybe it's one thread executing against the server, but it's one of something. And the scalability function begins at the origin and draws right through that point on the graph and continues out. And this is linear scalability. This is the mythical beast. When you walk by the vendor's booth and they say, our database scales linearly, they will show you a line on a graph. And what you should do is, just as a quick drive-by shooting of that vendor, which is really easy and fun to do, what you should do is take the top point and the bottom point on that graph that has a straight line drawn between it magically, and then just do a little bit of division to see if you extended that out, would it actually go through the origin? And most of the time it will not go through the origin, no matter how straight the line looks to your eye. Most systems do not scale linearly. Here's another system that's linearly scalable. What's happening here, what it means when we say linear scalability, is we're expressing that as we add more of something to a system, we get equal return on investment. We get equal bang for the buck. If we add 2 servers, each of those servers will linearly increase the capacity of the system. If we add 2 more threads, we will get twice as much more work done, right? So that's linear scalability. The difference between these two that I've charted on here is performance. And performance is orthogonal, independent to scalability. You can have a high-performance, linearly scalable system. You can have a low-performance, linearly scalable system. It doesn't change that they're linearly scalable or not. I'll just move on from that point, and I won't return to it. But here's not linear scalability. You can draw a straight line between these points, but it won't go through the origin, right? And here's another point. This is what typical systems look like. Typical systems don't scale linearly. In fact, there's only a few systems that I have ever I've never seen a linear or worked on a linearly scalable system myself. I've read papers about some, but I haven't actually been privileged enough to be in the presence of one. There's very few systems in the world that actually scale linearly. So what causes this degradation in scalability? Why don't systems scale linearly? There's 2 factors. The first factor is serialization. There's a portion of the work that cannot be done in parallel. So linear scalability would require that everything can be done independently and in parallel and perfectly subdividable. But most of the time, systems have some work that needs to be done in serial. I'll give you an example. It's MapReduce. You map something out, and you do a lot of it in parallel, and then you put it back together. Well, putting it back together happens in serial. So that portion of the work that has to be done in serial cannot be distributed. And that causes MapReduce systems not to scale linearly, unless that aggregation, again, at the end is infinitely small, which, of course, we know it isn't, right? The Amdahl's law expresses this portion of the nonlinearity. And the term on the bottom of this function has a sigma in front of it, and sigma is the portion of the workload that can't be, the fraction of the workload that can't be done in perfect parallelism. So workloads that, if you kind of plug larger numbers into this, into sigma there, you'll see that the denominator of that fraction gets larger, and therefore the system actually hits an asymptotic point past which it can't go. Another way of looking at this is to think of it in inverses. If 5% of the workload has to be done serially, then you can never reduce the total execution time below 5% of what a single-threaded process could achieve. Does that make sense? Okay. So the other factor can actually just be added to the bottom of this equation, and this creates the universal scalability law, which is a product of Neil Gunther, who was here speaking last year. He's a genius, and someday his name will be as famous as many other mathematicians. But for right now, this somehow seems to be not very well known. The second factor to nonlinear scalability is the crosstalk within the system. So if systems have to coordinate within themselves internally, be it inter-process communication, synchronization of a cache line between CPU cores, those kinds of things, there are lots and lots of systems that have to do some coordination or locking between themselves to make sure that they operate consistently on the data. And the cost of consistency, the cost of coherency, is the second factor here. And that we denote the fraction of the work that requires cross-node communication, we denote by the coefficient kappa. So if we plot all of these things out, linearly scalable systems are a diagonal line. Systems that have only some serialization but no crosstalk are an asymptotically ever-growing line. Systems that have some coherency problems within them actually reach a maximum and then they drop off. And this is what most systems really look like. If you're familiar with looking at benchmarks, there's usually a peak, and then there's a drop-off after the peak where there's actually a negative return on investment. If you push more threads into the system, you get less work done. If you add more servers to your cluster, you get less work done. And that models real life very well. There are other scalability models. Most of them do not have a basis in the physical realities of the system. For example, there's a quadratic scaling model, which goes up and then it goes down like real systems, but then it goes negative, unlike real systems. So you have to choose a model that actually matches reality as closely as you can. So from this model, which I assure you is infinitely simpler than queuing theory, if any of you has ever worked with the queuing theory equations, the Erlang C function in particular is the one that often comes up. This is way, way simpler. This means that it's actually accessible to ordinary mortals like me. It means that we can actually use it in the field, and there's not a whole lot of math that has to go on. I mean, this equation is not particularly complicated. There isn't even a root in here. It's just a simple fraction. One thing I want to mention, if we look at the kappa function here, it actually scales quadratically in the number of nodes in the system. That's why there's a decreasing return on investment, because as it gets large, the quadratically increasing contention within the system actually overwhelms the linearly increasing capacity of the system as you go to the right on the graph. That's why it starts to drop off and have a negative slope. It'll never go negative, of course, because we're only dealing with positive domain numbers here, but it will have a negative slope. So the scalability modeling method that we can use to actually model and measure and forecast system scalability is as follows. Measure the throughput and concurrency, which are the two inputs to this function. You perform a regression against the universal scalability law, and you determine the coefficients of the denominator as a result. And then you do something else, which generally requires having a contract with somebody with some money attached to it. And then you profit. So we can actually get this stuff from the TCP data, as I mentioned earlier. The concurrency is a little bit hard, but throughput we basically get for free. We just count the number of queries that complete or arrive in our observation interval. Now, it doesn't really matter whether we measure completions or arrivals, because all of this stuff is predicated on a long-term observation where in a stable system, those two are equivalent. If you have an unstable system, it'll queue to infinity. Like if things keep arriving but never actually complete, it'll queue to infinity. But most systems are not like that. And in most systems, you just make your observation interval large enough, and maybe you then throw away some data from the beginning and the end where you didn't get your observation beginning and end period bisected some portion of the workload that you were observing, and then you have something in the middle that represents a stable, long-term state of the system. So what we do to gather concurrency is we sort the arrivals and departures in order, which is important. And then each arrival increments the concurrency 1, right? A query starts running, and that means that there is one more unit of concurrency within the system. And then when the query completes, you drop the concurrency down 1, and then you calculate a moving weighted average as time proceeds. And here's a picture of that. So query arrives at t equals 0. That's Q1 in the first blue box. I should have color-coded them. And while it is executing, at t equals 2, a second query arrives, Now for just a brief period here, the concurrency on the system is 2. Then query run 1 completes, and query 2 runs to completion at t equals 7. So the total observation time is length 7. Let's just make all of these units in seconds. It's 7 seconds long, and the total query time within that observation interval was 8 seconds worth of execution on the server, which means that the concurrency within this period of time was 8/7. So this is how we can actually determine the real concurrency on the system. So we can compute this with the PT TCP model tool again. First, I'm just sorting them in arrival order. The reason I sort them in arrival order is because otherwise you need to have a very expensive algorithm to figure out how much concurrency there was at any point in time. So sorting makes the algorithm relatively trivial. It's only a few hundred lines of code that actually compute this. And after sorting it, then I run PT TCP model again on it, and this time I'm giving the -- type equals requests argument to it. And you can also change the aggregation interval, but by default it's going to slice things up into, I believe it's 1 second intervals. I've forgotten what the default slice time is there. And it prints out lines to a file again. I wish I'd shown you the actual lines that it prints out. And then this is the input that we need for the universal scalability model. And we can plot these points and fit the model to the points, and we get the universal scalability model coefficients out of it, and then we can draw the graph that corresponds to that. So what we have on this graph is a whole series of computations, including the outcomes. You can see that the points are plotted in a scatter plot with concurrency on the x-axis and throughput on the y-axis. And then the red line is the universal scalability model fitted to that data. This is not particularly clean data. I have seen much cleaner data, specifically on systems like Oracle that are perhaps better behaved than MySQL in complex workloads, but also on real hardware instead of the Amazon EC2 platform where everything is constantly varying and you're contending with other systems for system resources like network throughput and those kinds of things. The sigma fraction here, the serialization within the system, turns out to be about 2.8%, and kappa, the crosstalk within the system, is 0.3%. And then there's, underneath of that on the chart, there's the R squared, which shows how closely the model fits to the data. This is not bad. I mean, it's 98.5%. I've seen much better. I'd like something that's like 3 or 4 nines in a row there. But the statisticians will still tell you that 98.5% shows that the model is highly correlated to the data. And the green points are, of course, the measurements that came out of this sample of TCP traffic. Any questions before I move on from this point? Okay. Thought I saw a hand, but it's just leaning against a pillar. So the next thing that we can do is we can model performance. This models the scalability of the system beyond what we can observe. Actually, let me belabor this point a little bit more, belabor this slide a little bit more before I move on from it. The first points close to the axis there, you can see they lie relatively close to the red line, and they appear to be fairly clean. As we get further out into these higher concurrencies, what is that, like 6, 7 concurrency, maybe of 8, something like that, it starts to scatter out a little bit more, and it's definitely not as clean. It doesn't fit the model as well. That's because this system is starting to behave badly. We saw bad behavior earlier with all of those different kinds of spikes on the line. This is another way that we see bad behavior. Systems that behave well tend to actually plot pretty well along the line. And what this means, although the model predicts, and the tool that I use here, a set of scripts around GNU plot, actually says that it thinks the peak capacity is going to be 3,600 queries per second at a concurrency of 13. I can tell you we really ought not to be pushing things up that high on this server because we're going to get really bad quality of service. We're going to be getting those variable response times. We're going to be getting spikes and stalls and all of that kind of stuff. So at this high of concurrency on this server, we're seeing basically we don't need the model. The data itself tells us you're basically getting all you can out of this server. And indeed, this server next week it's actually going into an on-premise server with much more horsepower. the server was maxed, and we had many, many, many performance problems with this server that were just unsolvable. No amount of tuning or query optimization or indexes could really improve this server's workload. So although it's interesting to model this, it doesn't, in the end, tell us anything that we didn't know. I mean, we can't actually use this particular red line to forecast the scalability of this system. However, in other cases, you can. And I'll show you a little bit later the 2 ways that you can actually use that in real life and what it really means. But before we do, performance. Performance is response time. So this is, again, a definition that we can agree on and we can actually use. We don't have to sort of talk in vague terms about it. And Little's law lets us calculate the response times in case we didn't already have them, which we do. But Little's law lets us calculate that even if we only had the throughput and the concurrency of the system. And so all we have to do is use this little relationship, and we can flip the chart upside down, essentially, doing the inverse of the chart relative to concurrency. And we can model the performance of the system beyond what we can observe as well. So we can start to answer questions like, how much more workload can I put onto this server, not just before it reaches peak capacity, but how much more work can I put in this server before my response times become longer than a certain point, which may be a constraint that you have in your application. You know, maybe this application is doing AJAX requests, and you want to make sure that they all complete within a certain response time, or maybe you're bound to a particular service level agreement because you're serving advertisements, and if you don't serve it quickly enough, the opportunity is lost, and your contract with your partner penalizes you. Those kinds of things. So you can actually model how long queries are going to take to execute beyond what you can observe. And we see the same kind of a thing here with the response times. The points on the graph starting to cluster, or clustering a little bit, but not clustering as well as we experience increased concurrency. So things get more chaotic, more variable as we load this server more heavily. So you need to be careful with this. If you throw garbage into the system, you will get garbage out. And it's highly likely that if you go try this on your own systems, you'll get some garbage in, garbage out for a little bit. It takes a little bit of experience. This really isn't rocket science. There's no secret magical recipe that I have. Just a little bit of experience and intuition, and sometimes you may need to clean up your data a little bit. There's a few things that you need to do. In particular, you need to be aware of dropped packets in TCP dump. In the future, I'm going to write a tool that plugs into libpcap, so that I don't have to use Perl scripts on top of TCP dump and all of those kinds of things, so that I can look at the sequence numbers of the TCP as well, and I can make sure that I'm correlating the right response with the right arrival. If you have TCP dump dropping some packets, there's a chance that a packet comes in, you miss the response because the kernel throws that away before TCP dump gets it, and you correlate the later response wrongly and generate a long-running query that never actually happened on the system. So you need to be aware, when you run TCP dump, you got to watch for dropped packets. And if the system is loaded too heavily, or if you have your TCP buffer set too small, or those kinds of things, you can actually get a lot of dropped packets, and you just get utter noise. As an example, I ran the same technique on a server that was a much more powerful server, not in the cloud, with tons and tons of, 3,000 queries per second, that's wimpy, right? This thing is cranking tens of thousands of queries per second out because it's on a nice, powerful server. And we're really throwing some work through it. And TCP dump can't keep up at all. The kernel drops packets left and right. And I can look at the server, and I can see that there's 1, 2, 3, 4, 5 queries running at a time. But if I run this model on it, it goes, your concurrency is 300. Well, that's obviously bogus, right? So in that case, this model technique doesn't apply. So you have to look at the data and make sure that it makes sense. You may also need to remove outliers. Somebody mentioned cron jobs earlier. If cron job starts up in the middle of your workload, well, first of all, you're going to be plotting it by time series, right? So you should see a really distinctive bump or a sag in your graph. And you should be able to say, well, that portion of my data is no good. Slice it out, throw it away, right? Look at good, clean data over a nice uniform workload, the workload that you want to actually predict. Don't mix it in with your cron jobs or your RAID controller starting a patrol read or any of those kinds of things. Okay? So there are 2 ways that this kind of modeling is useful. And I'll show you specifically the universal scalability law throughput modeling, the scalability modeling, not the performance modeling. And you can use it as worst case bound and as a best case bound. So a worst case bound is very useful for finding scalability problems in systems and being able to have a conversation about whether the system is scaling as well as it should. Okay, so bottleneck analysis. The worst case scaling model that the universal scalability law embodies is something called synchronous repairman queuing. And that is, again, truly worst case scaling. It assumes, for example, that all of the nodes within the system are doing some crosstalk with each other. But in some systems, that may not be true. In a highly distributed system, you may actually only need to talk to one other node in the system, not all of the other nodes in the system, right? So your system should scale at least as well as the universal scalability model, in theory. If it doesn't, something is broken, which is always true. Systems never really scale like they're supposed to, right? So if it doesn't, you can go and you can ask, what's happening here? If you didn't have a model, you wouldn't be able to ask what's happening here. You would just go, oh, hey, pretty graph. Right? You wouldn't have a basis for this discussion. The other thing to be careful of, here's our double rainbow. What does this mean? The other thing to be careful of here is don't just look at a graph and go, whoa, the shape of the graph. You also have to look at the units on the graph, because this graph, if you look at it, it actually curves up before it starts to curve down again. The universal scalability model doesn't do that. It only is concave downwards, right? So what's happening there? If you look at the units along the x-axis on the bottom, we don't even have a logarithmic progression of units on the bottom. We have things graphed at the same distance apart that are not the same magnitude apart. We go 1, 2, 4, 8, 24, 32. That's not even powers of 2, right? If it went 1, 2, 4, 8, 16, 32, that would be sensible. But as it happens, 1, 2, 8, 24, 32 is where these points actually lie on the graph. So you have to be careful about that. Most graphs of benchmarks that you see actually will have some logarithmic scaling on the x-axis, and that's why you'll get a different shape than you're used to. So the worst case bound is one way that you can look at the scalability model. Another way is best case bound. So you can apply this to your real system, and you can do capacity planning. So you can say, I have these points on the graph, and if I assume linear scalability, this is a mistake that I've seen some people make. If I assume linear scalability, it looks like, to reach this point in my projected work or to handle this much more, or all those kinds of things, I can just, looks like I can just add a few more servers, maybe just add 3 more servers and handle 3 times the workload. And that is unrealistically optimistic. So although the universal scalability law is a worst case scenario, you should always assume that your servers are not going to even behave that well, right? Because systems are not perfectly scalable, even according to the synchronous repairman queuing model. So you should model it out and you go, here's what's really going to happen, or this is the best that I can count on. This is the best that I can responsibly for my business count on. So it looks to me like we have a problem here. We're going to run out of capacity sooner than I would really like to, and I can't count on just adding 3 times the number of servers and getting 3 times the throughput. Okay? So here's the summary, quickly. We can capture these arrivals in TCP, arrivals and completions from TCP dump, and measure the query performance easily. This we get for free just by subtracting. We can plot that. We can find problems that the eye can't see by doing a little bit more math on it in a few different ways. And I imagine that with the creativity in this room, if we all went off and spent a few hours, you'd probably come back to me and go, hey, I found another really cool metric. Add this to your slides for next time. But the 4 ways that I showed you to plot this are some very good ways to dig in and see whether things are going badly, or just to see how badly things are going, because something is always going badly, right? We can forecast this out beyond what we can observe for nearly any system. This works for MySQL, it works for PostgreSQL, it works for TCP, on pretty much anything. Apache web servers, all kinds of stuff. You can actually do this at the level of an entire system. So you can measure how your whole application behaves. And you can do this on systems that have 0 instrumentation. So you don't have to gripe anymore about how the system doesn't let you measure. You can also do this on systems where you may not have access to privileged data. You can ask the system administrator to go and capture some packet headers for you. Anybody who claims that packet headers are privileged information is really, really, really strict. But you can do this on systems where compliance requirements are very high. And finally, to actually get useful value out of this, you need a little bit of experience. Try it. Play with it a little bit. If you don't get good, if you just get this big blob on your graph, look at your data and see what's going on. You may have dropped packets. You may have a two-variable workload. You may have measured something wrong. You may not be scoping your measurements correctly, so you might be overlapping with different things happening on the system. And the answers are not exact, but they can be used as bounds, lowercase bounds and best case bounds. Here's where the software that you can get to help with this modeling. It's part of Percona Toolkit. PT TCP model. That is so hard to say. And here's further reading. This is Dr. Neil Gunther's book, which is a work of genius, but it's also very dense and difficult to understand. So I condensed it into a white paper that lays out not just sort of what the model is and why it is what it is, but does the math very simply and then shows you pretty much some of the same stuff that I've talked through today as far as the scalability modeling part of this talk. And I'm happy for questions now. I'm happy for questions by email later. You can always find me at baron@percona.com. And we've got 5 minutes. So any questions? Yes, sir.
This sort of assumes that DBA is talking to other people. Have you thought about what you can get from that flow? Because I mean, just looking at TCP headers, you should be able to get a lot of those from that flow. So you have a real value.
Yeah, so the point is a lot of times DBAs and network people don't really talk to each other, but you can do this, at any point in the system, you can capture the flow. You can do this on the database server, which is probably the most accurate place to do it, because when the query arrives at the database server is where it's very close to when it arrives at the network interface. There's not that much delay there. You can also do this, however, from the client machine. If you don't have access to the database server, you can actually run this from one of the web servers where the packets are originating. You'll add in some extra latency for the network latency, so it'll look like the queries ran a little bit longer than they did on the database server, and that'll inflate your concurrency a little bit. But it's still very useful for a lot of these kinds of analysis. Yeah. Yeah. So the comment for the folks who are watching the video is that this gentleman is a network engineer and captured this stuff from the switch, and everybody loved it because it gave him a lot of insight and visibility into the system without adding load on the systems. I will add a note here. TCP dump typically only adds 1% or 2% of CPU consumption to a system, so relative to a lot of other instrumentation, it's very lightweight. However, I believe in the value of instrumentation. If the overhead is 10%, if the overhead is 20%, and it gives you the data that you need to make the system 10 times faster, then the overhead of the system doesn't slow the system down, it makes it faster. So just sort of a comment on that. So you kept all the data? Okay, great, yeah. Yeah. So again, just to repeat that, there was a month worth of data. That's great. Yes, sir?
What would happen if you tried to use this toolkit on a web server and see pipeline requests? Keep track of that?
So the question is, what happens if there's HTTP pipelining? I'm actually not sure. That's a great question to investigate more. Yeah. What's that? Yeah. So I need to wrap up for the next person. Thanks, everyone.